Friends, recently I came across a library called String to String in the natural language space. It's developed by Stanford University. It's quite good. It has some old as well as the recent algorithms to compute the distances between the strings, similarity between the strings, to check how they align with each other, which is commonly used in bioinformatics, as well as some search capabilities. And then it also has the embeddings functionality so that we can use it to build semantic search engine, etc. Okay, so first we look in the first 4 videos, we look at different functions to compute these 4 things, and then we will build 2 applications. One is to check a plagiarism, and the next one is to do a similarity or the semantic search engine. Okay, all right. So today we will look at the distance. So basically, we will measure the distance, which quantify how dissimilar 2 strings are from one another. Okay. All right, here is the formal definition. It's the problem of quantifying the extent to which 2 strings are dissimilar to each other based on some distance metrics, right? This distance metric can be different. So here we have 4 methods. We are going to look at all those 4 methods. Now, you probably already familiar with Levenshtein's distance, which is commonly used for these type of applications. Now, the important thing here is, so the insertion, deletion, and substitution. Okay, so let's say we have been given 2 strings. Now, to convert one string to another, for example, string 1 and string 2. Now, to transform this string 1 to string 2, how many insertions, deletions, as well as substitutions we need to make? That's called a Levenshtein distance. Okay. So using this library is quite simple. After doing the pip install or conda install, you can do this string. You can load the library string to string, and then the functionality. This can be either distance or similarity, etc. And then the algorithms. So the first one is this Levenshtein edit distance. Okay. So here we have 2 strings. The first one, the quick brown fox jumps over the lazy dog, right? In the second one, we have some typos. For example, here you can see instead of Q, here we have K. Okay, and then instead of I, we have A, and there is one more somewhere here. Instead of fox, it's a box. Okay, so let's see. So we can either do insertion, deletion, or substitution, right? We are allowed to do these 3 operations. Now, to transform this string 1 into string 2, we need to replace the Q with K. Okay, so that's 1. We need to replace I with A. That's number 2. We need to replace F with B. That's 3. Okay, then the remaining characters are exactly the same. So the Levenshtein distance should be 3. Okay. Now, over the couple of cells, we are just computing how much time it would take to compute this matrix. That's not important. That's just to show you different algorithms can compute this Levenshtein distance. So we'll show different algorithms take different amount of time. But by default, without supplying what algorithm we use, it uses the most optimized algorithm. So we don't need to really worry about this additional optional parameter. Okay. All right. So yeah, here we have loaded this Levenshtein distance module. We instantiated it and simply do the edit distance, and you call the compute and you supply these 2 strings. Okay. So it says the distance between these 2 strings is 3, as we have seen here, right? So we need to replace 3 characters. We need to substitute 3 characters, one here, and one here. Okay. All right. So the distance, the time it took is some 0.008 seconds. Okay. Yeah, as I just mentioned, there are multiple algorithms which can compute this Levenshtein distance. For example, one of them is this recursive method. Now here we are taking 2 simple strings so that we can compute much quicker. So using this recursive distance, recursive algorithm. So it took 0.6 seconds, and let's check. So within these two strings, here we need to replace this E with P and P with E, right? So the Levenshtein distance is 2. All right, that looks good. And then there is another method called recursive memorization. I mean, the answer is just 2, as you can see, but this took a lot less time, right? It's 0.00016 seconds. And the default algorithm, which is this Wagner-Fish algorithm, used by this function, when we did not supply this, it actually used this Wagner-Fisher algorithm. Okay, so this also computed in just 0.0015 seconds. So among these three methods which can compute the Levenshtein distance, this Wagner-Fisher algorithm is the most optimized one. Okay, a quick recap. All we are doing is we are simply from the functionality, we are exporting the particular algorithm, and we instantiate that algorithm, and we simply supply the two strings to compute the distance. Okay, so that's Levenshtein distance. And we can also do a weighted Levenshtein distance. So as we saw here, we are doing either insertion, deletion, or substitution, right? Now we can provide different weightage. I mean, by default, we are saying everything has equal weightage, right? We are which is 1. But we can also have this weighted distance, where we can supply how much weightage we want to give it to insert, delete, and substitute, right? So here we are saying probably, I mean, it's something like, okay, inserting and deleting is more costlier or more expensive than, let's say, a substitute, right? So we are giving low weight to substitute. So here we have two strings. Let's see. Both of them have equal length. So this is one character, this is second one, this is third, this is fourth. So we need to do 4 substitutions, right? We need to do 4 substitutions, and that's why we got the answer as 2. So here in when we instantiate, we can supply the weights, and when we compute the distance, these weights are taken into account. For example, let me do this. Let me introduce another character. So this time it should be 3 because 2 already there, and we have additional character which need to be deleted. So if we do this, yeah, so we got the distance as 3. And the third one, this Damerau-Levenshtein distance. Now, in addition to insertion, deletion, and substitution, we have another one called a transposition. Okay, we can swap the characters from different positions. Okay, so which means this Damerau-Levenshtein distance will be shorter than the classical Levenshtein distance, right? Because here we can do additional operation. So let's do here. For example, here we have again 2 strings. I mean, using it is very similar. From the distance, here we are picking up the second algorithm, and you instantiate the algorithm, and you simply call the algorithm on the 2 strings. So for the classical Levenshtein distance, we need to replace E with P and P with E. So that would be 2, right? Whereas in this algorithm, since we can do the transposition, we can swap the characters. So for example, let's say we swap E and P, we would arrive at string 2. So we need to make only one transposition. So this distance will be equal to 1. Okay, yeah. And finally, Hamming distance. Now, all the previous computes, they work irrespective of the size of each string or the length of each string. Whereas Hamming distance, it only works if we have both the strings of similar length. For example, let me do this. So as you can see here, string 1 has 1 character more than string 2, so it raises an error. Okay, must have the same length. So Hamming distance work only when both the strings have same length. And then Hamming distance is simply how many places where we have not matching characters. Okay, because we have strings of equal length, we can do one-to-one comparison. We don't have anything left out or additional in string 2. So if you look here, 1 and 2, so there are 2 spaces or 2 characters are two positions where the characters are different. Okay, so if we compute this, this distance, Hamming distance is 2. Okay, now Jaccard distance is probably the most useful one among these 3 algorithms we just discussed. The reason is it can work on documents or a list of strings. Okay, I mean, even when we have a document, we can use some tokenizer to create the words or tokens, and then we can use them as a list of strings. Okay, using this, we can measure the document similarity, or we can do the topic modeling, right? Let's say we have 2 different books, or maybe we have a book with different chapters. Now we want to compare we want to find out which 2 chapters are more similar to each other compared to the rest, right? And even within those 2 chapters, what are the topics emerging, etc. We can do that sorts of analysis. So Jaccard distance is much more useful. So yeah, as it says, we can find out the 2 different documents, how similar or dissimilar they are from a collection of documents. It's the same way we use. Here we have some 3 documents, and we instantiate the algorithm and we use the compute. Okay, so among these 3 documents, the algorithm says document 193 are more closer to each other compared to the other 2 combinations. Okay, so this score will be between 0 to 1. 1 means they are absolutely similar or identical. 0 means they are very different from one another. Okay, all right. So coming back to Levenshtein distance, earlier we have computed it only on 1 string or 1 word, right? But we can compute the Levenshtein distance again. It can be a document, meaning it can be a paragraph or some long form of text, or it can be a list of strings. Okay, so here we have 2 lists, and again we are computing the distance. Now this time it will treat each word as a separate entity. So it's not going to compute character by character. So among these 2 lists, here we have 1 word which is different, quick, and this one, and the second one, fox and box. The remaining characters are same. So here what we are calculating is between the distance between these 2 texts at the word level. Okay, notice that this is at the word level. Okay, the distance is 2 because we have 2 words which are not same in these 2 lists. Okay, and we can also do this at the character level. Okay, now here we have text unlike the lists here. Now obviously we can compute the distance at the character level. So this, I guess we have used this example before. So at the character level, the distance is 3 because we need to replace 3 characters, Q, U, and F, Q, I, and F. Now if we compute the distance at the word level, all we need to do is we just use a tokenizer and we inform the tokenizer, hey, split this text based on the space character. Okay, so here we have tokenized text, and now we compute the distance. So by default, because we are supplying a list, it compute the distance at the word level, which is 2. Okay, that's about it. As I mentioned, these can be used to compute the document similarity, which is very useful in topic modeling, etc. It's a very simple tutorial. And in the next 3 tutorials, we will compute the similarity, alignment, and search. And finally, we'll build 2 applications. One to detect the plagiarism, and then we build a semantic search engine using some complex documents. That's all for this video. Thank you very much.